Engineering Innovation at UCLA, an HHMI professor with the Howard Hughes Medical Institute. He's leading the Bio and Nanophotonics Laboratory at UCLA's School of Engineering. He's also the Associate Director of the California Nanosystems Institute. He's elected Fellow of the National Academy of Inventors and holds more than 50 issued and granted patents. Author of one book, co-author of more than 800 peer-reviewed publications in major scientific journals and conferences. He's a founder of many companies, including Busandi, HANA Diagnostics, Pictor Labs, Holomic Celmic LLC. He was named a technology pioneer by the World Economic Forum in 2015. He's a fellow of American Association for the Advancement of Science, the International Photonic Society, the Optical Society of America, the American Institute for Medical and Biological Engineering, IEEE, the Royal Society of Chemistry, American Physical Society, and the Guggenheim Foundation. He has many awards, but if I list them, it would take too long. So with this, Aydogan, you have the floor.
Thank you. Thanks for having me today. Thanks for the invitation, and it's great to see you all. So today I'll talk to you about some of our recent work on the use of deep learning for computational microscopy and sensing. So my lab has been, for the last almost 15 years, has been working on creating mobile, cost-effective technologies for global health-related applications to bring advanced measurement tools to resource-poor settings and performing the same functions with the same resolution sensitivity that you expect from their lab-grade counterparts. And what you see here on this slide are some examples. It's been a routine to convert the cell phone into an advanced microscope, a bright-field microscopy, coherent quantitative phase imaging, fluorescence microscopy can be integrated easily, cost-effectively with smartphones. It's come a long way. Maybe when we first started this line of research, 15 years ago, you could barely see a red blood cell, but these days you can actually even see individual viruses and even DNA molecules. For example, this one that I'm sharing here with you on the slide, it's a fluorescence dark field microscope where with an inexpensive attachment to the back of a smartphone, you can actually see individual stretched DNA molecules. This is silane chemistry, simple stretching of double-stranded DNA with also labeled with intercalating dyes. And you can see, for example, this one is a benchtop microscope, diffraction limited, and this one is the cell phone showing you the DNA molecules that are fluorescently labeled over a very large field of view. You can also combine this to have multimodal microscopy, where, for example, in this case, you're having a bright field microscope and a fluorescence microscope that can image at two different color channels on the same embodiment. So this is a multimodal microscope. In collaboration with a Swedish group, we have used this to read basically DNA sequencing, targeted DNA sequencing, and in situ mutation analysis using rolling circle amplification. Basically, as RCA proceeds, you have clusters of DNA, and we've labeled them with two different colors for mutant and wild type. And we've shown that using colon cancer patients, you can actually perform targeted DNA sequencing on the tissue level and image them with these mobile phones as the basis of the readout. So as I said, it's come a long way, barely from seeing red blood cells down to individual viruses, bacteria, and even single molecule DNA, and size them with about 1 kilobase pair sizing accuracy sufficient for example, understanding replication of genes for drug resistance related applications. So it's really very exciting times. In addition to converting the smartphone into advanced microscopes with add-on optics, we also sometimes take the CMOS imager, the silicon chip off a smartphone and build microscopes around it. These are handheld computational microscopes. For example, this one here on the left, this is a computational lensless microscope that is as tall as an iPhone and perhaps 150, 200 grams in total weight and it can actually achieve diffraction-limited imaging of transmissive samples like tissue slides over a very large field of view on the order of 20-30 millimeters square. If you look inside one of these computational lensless microscopes, this is not your father's microscope, so to speak. The sample goes here. It's a transmissive microscope. Think of it as a blood smear, pap smear, tissue specimen. It goes directly on top of a CMOS imager. This is the same 510 megapixel that's coming from your smartphone. And there's no lens between the sample and the CMOS image. So you directly record partially coherent holograms of the specimen sampled with a CMOS imager. There's some illumination optics here, very inexpensive, composed of LEDs. You turn them on and off to create pixel super resolution. The technology behind this is very much like how some security cameras operate. For example, if the person is slightly jittering because of the cameraman's hand, or if the person is moving, you can actually take these individual diffraction-limited images, pixel-limited images, and resolve sub-pixel level details using pixel super resolution and optimization framework that divides each pixel into sub-pixels. This is exactly what we do at the micro scale using lensless microscopy, holographic microscopy, where you take the CMOS imager with unit magnification and divide these individual pixels of the RGB pattern, Bayer pattern of the CMOS, and create deeply sub-pixel resolution on the order of a few hundred nanometers, considering the fact that the original pixel size in this case is about 1.1 micron. You can clearly understand that this is giving you more pixels. You can actually have here approximately 1 billion useful pixels looking at a field of view of approximately 20 millimeters square. And you can change the CMOS imager and make it even larger field of view on demand. So this is a portable, inexpensive computational microscope, and it would be especially very valuable for telemedicine applications, looking at specimen in resource-limited settings, and certainly portable. One of the first applications we've looked into using these kinds of lensless on-chip microscopes was looking into thin smears, thick smears. This is a thin smear of malaria red blood cells infected with malaria. Plasmodium falciparum. For example, this is a traditional light microscope, Giemsa stained slide, and these are the signatures of the parasites. The lensless microscope captures the same field of view with beautiful resolution and reveals through the phase channel, because these are coherent microscopes. They have phase and amplitude information of the specimen, so you can have some beautiful contrast of the Plasmodium falciparum and the crystals it generates, hemozoin crystals it generates through the phase channel, giving you some beautiful contrast. But the biggest advantage, in addition to being cost-effective and portable, for these microscopes is actually field of view. You can look at a very large area, pardon me, you can look at a very large area of a smear. These are some white blood cells, red blood cells. Zoom in and see the count of these infections across a very large field of view. For malaria, microscopy is still the gold standard for peristemia. So even for diagnosis and for therapy, you need to look into the count of these parasites. And this is where an inexpensive, high throughput, wide field of view microscope is very useful. Here I'm sharing with you an image of a tissue specimen. This is a breast tissue section. The field of view advantage of lensless microscopy is also highlighted here. A traditional objective lens would be looking at, for example, a 40x objective lens with 0.8, 0.7 numerical aperture would be looking at this kind of a field of view. So you would have to scan a few hundred of these images to digitally stitch one of these large fields of view. Lensless microscopy can get that in a single shot because of its large field of view. These are this is the large thin section. It's 3 to 4 microns thick. If you look at individual holograms, these are what you see. Not easy to understand what's going on because these are holographic interference patterns. Only after reconstruction you can see the subcellular features of tissue, which nicely matches to a traditional light microscope, except this is lensless and all compact. You can also bring color to this holographic system by using red, green, and blue LEDs or laser diodes simultaneously on and benefit from the Bayer pattern, the RGB pixels on a CMOS color imager. For example, this one is a lung pneumonia sample imaged with a lensless microscope, showing again the field of view advantage of lens-free microscopy. You can zoom in and reveal various different features from a large field of view. You can continue zooming in and reveal these fine features of the specimen coming from basically the RGB channels of illumination. Whatever I've shown you today so far was obtained with a CMOS imager, literally coming from a smartphone. These are the CMOS imagers that our smartphone utilize. Typical field of view is shown here. This is the active rear of the CMOS. Perhaps 5 by 5 millimeter is a good number to keep in mind, half a centimeter by half a centimeter. But you can also use CCDs, charge-coupled devices, for the same platform. This platform is unique in the sense that field of view or sample volume is not tied to resolution. If you have bigger area sensors, larger megapixel sensors, you can actually increase field of view and sample volume without a trade-off in resolution. Here you're looking at a field of view of 18 centimeters square with a CCD that has a native pixel size of about 7 micron, but through pixel super resolution, you have a resolution of approximately 2 micron across this whole image. You see here about 1.5 billion useful pixels. These are raw holograms. Reconstructions are shown here. These are human sperm cells where the tail, the flagellum here is shown. Typically, at some point, it's a sub-micron feature here in terms of the width of those flagellum. So in addition to microscopy, my lab is also very much interested in sensing, utilization of mobile computational interfaces for sensing, all the way from sensing of bacteria, cysts, giardia, or other kinds of waterborne pathogens, to heavy metals, and other kinds of analysis can be done with systems that are integrated with smartphones, cost-effectively built. So I won't talk more about this line of research, but another very exciting area for utilizing smartphone as a platform is sensing, computational sensing. And we've done some tremendous amount of work here, especially on the utilization of deep learning for multiplex sensing. So if you want to reach out to some of our work on vertical flow assays and utilization of multiplex sensing capabilities in vertical flow assays for a quantification of the panel of analytes, or looking into IgG, IgM patterns, such as, for example, Lyme disease diagnostics. It's a very exciting and recent area of research coming from our lab. So after this very brief intro to some of the past work that we've done, I'd like to come to today's topic of how we have been utilizing deep learning in our quest for enhancing microscopy, advancing microscopy. So, of course, deep neural nets have been used for image segmentation, classification, and various different machine vision tasks. But here in this talk, I'll be specifically interested in showing you examples of how we used it for image reconstruction, image transformations, to take one mode of microscopy and reconstruct its image as if it's coming from another mode of microscopy, or to use it as a reconstruction engine for computational imaging, holographic imaging. That's essentially the topic of what I'll present today. Deep neural nets are universal function approximators. They're trained using various different tools based on error backpropagation, but you can think of it as a function approximator. The training is one time. It may take quite a bit of time. You may be asking, how many images do you need to train one of these architectures? Well, it will be tens of thousands, and depending on how fast you can acquire these, it might take a week, maybe sometimes more, but doesn't matter. It's a fixed effort. It's only one time. After you're done with optimization of that neural net, the inference is extremely fast, and it happens in a single feed-forward manner. Traditional image reconstruction methods before neural nets became popular are always almost iterative. So you guess a solution and you correct it iteratively. So this iterative nature of traditional image reconstruction methods is probably one of the biggest disadvantages that we have seen over the last several decades in terms of fidelity and reconstruction speed. And that's where neural nets have made a big impact by making this whole reconstruction faster and better, and also sometimes exploring a domain that we could not explore before because the physics of the forward propagation or forward model was not available in some transformations. I'll give you examples of this throughout my talk. So literally, you can take a deep neural net and train it with image data and use it for various different tasks in microscopy. You can take a hologram and reconstruct it as traditional physics-based reconstruction methods normally reconstruct. You can learn from physics and do holographic reconstruction. Our lab was the first to apply deep learning to holographic image reconstruction to show microscopic details can be reconstructed using a neural net, creating an alternative to physics-based creative reconstruction methods. And these types of holographic reconstructions performed using neural nets enabled us to bring more power to our mobile instrumentation. So these are some examples of mobile imaging systems, computational imaging systems that are powered by deep learning. For example, this one over here, this is an imaging flow cytometer. It's a label-free imaging flow cytometer. It is based on holography and deep neural nets reconstructing those holograms without stopping the flow. As the objects, large objects, are flowing through a channel, we're capturing holograms in color without any labels and reconstructing them easily using a simple laptop on demand in real time. These are plankton particles captured from Los Angeles coastal line that are flowing with perhaps a centimeter per second speed at a throughput of 0.1 to 0.5 liters per hour. Without stopping flow, you can beautifully create microscopic images of these plankton. This is enabled by lensless microscopy reconstructed using a laptop by neural networks. This one is already commercialized through a startup that I have, and we believe especially for looking into algae blooms, this will be very useful. It's cost effective, it's like a shoebox, perhaps 1 kilogram in weight, perhaps slightly larger than that, but it's certainly serving the needs in field settings to screen for dynamic changes in, for example, a lake or the ocean that you are having your fish farm, etc. Similarly, we have been very much interested in utilization of holographic microscopy that is enhanced with deep learning for looking into particles, particulate matter in air, and allergens in air. This one is a device that we call C-Air. It is powered by also a Lensfree microscopy that I've outlined in the first part of my talk. This is the inlet, which takes perhaps 13 liters of air per minute in. Let's say if you run this half a minute, you take 6.5 liters of air and deposit on a transparent substrate. You capture holographic images before and after, reconstruct them using deep learning. And another set of neural networks are helping you to classify different types of pollen, allergens, and mold. So we've shown that you can achieve more than 93% classification accuracy in a label-free manner with this kind of a scheme for looking into different kinds of pollen and black mold particles without any labels, just based on spectral and spatial features of these objects captured with a lensless microscope, reconstructed with deep learning. So these were examples of how deep learning enhanced reconstructions have been helping us with our mobile instrumentations and sensors. And you can argue that almost all of these reconstructions could also be done with standard hologram reconstruction methods, phase retrieval methods, which is true, but deep learning is faster and without any iterations. But there's more to this story. And what I want to share with you right now is how you can actually reconstruct holograms in unique ways that are not possible with standard physics-based reconstruction methods. Here, we're going to take a hologram and train a neural network to reconstruct the holograms, raw holograms, with the contrast, spatial and spectral contrast of bright-field microscopy. This is very challenging because holography is single frequency, single wavelength, and bright-field is broadband. And at the same time, the contrast mechanisms, light scattering and contrast mechanisms of coherent imaging and incoherent imaging, like Brightfield, these are not easy to model as a forward model to be inert. That means physical understanding of light matter interaction is not helping us to establish this transformation of a hologram into bright field contrast. For the first time, actually, we've done this through data by capturing with a bright field microscope many images of specimen, while at the same time the same specimen were imaged with a holographic microscope. We were able to register in 3D holographic projections to bright field scanned images, so that you can actually learn through image data, microscopic image data, this transformation. Although you do not have a full physical understanding of it. This is where image data helps you. It helps you extract some of those correlations that otherwise you do not have a physical understanding of. After this training process, you can actually have a hologram reconstructed with bright field contrast. This is the best of both worlds because bright field microscopy is great. It gives you a color contrast, beautiful rejection of different planes without any speckle noise. But bright field microscopy is bulky and it has to scan in 3D. So now you can actually have a hologram replace that. So these are pollen particles that are imaged with a holographic microscope. This is how the standard reconstruction would look. You will have speckled pattern and some other artifacts because of coherence of holography. This cross-modality transformation network reconstructs the same holograms with the contrast, color contrast, and spatial contrast of a bright field microscope. And this is a standard bright field microscope giving you the same results. This is the first time that holography, a hologram, was reconstructed with bright field contrast, eliminating speckle and other artifacts, and benefiting from the advantages of holography. So this is also a movie showing you a single hologram on the left. So this is a single hologram that is virtually backpropagated to different heights within a specimen. And this is the neural net's output. And this is a scanning microscope comparison. So the far right movie is physically somebody scanning the microscope in 3D. And this is virtually what the neural net is output to. As you can see, even as the objects are getting, these are pollen particles captured in 3D, even as the objects are getting in focus and out of focus, you have a beautiful contrast, a nice comparison to standard bright field microscopy. So this is a volumetric reconstruction from a single hologram with the color contrast and spatial contrast of bright field microscopy. So these are not possible with standard physics-based reconstructions, and that's where it highlights the power of learning through image data, especially for microscopy, because microscopes are very repeatable. You can take this idea to some other extremes, and you can take similar learning principles and do cross-modality image transformations to achieve super resolution, beat the diffraction limit of light. In this example, we'll take confocal microscopy images that are diffraction limited and establish a transformation to a nonlinear microscopy modality that beats the diffraction limit of light, SLID microscopy, stimulated emission depletion microscopy, and show that you can actually do frequency extrapolation and get more information through the neural net for a given field of view acquired with a diffraction limited microscope. These are blind testing data. Whenever I'm showing you a network inference here, it's always blind testing, which means the training is passed, the network is fixed, and I'm sharing here results from unseen new data, new objects, new cells. These are HeLa cell nuclei, confocal microscope images at the input. It is diffraction limited, it's got beautiful contrast, but some features are lost because of the diffraction limited light. If it passes through the super resolution network that is trained against SLID microscopy, to mimic SLID microscopy, you see all those features coming back. Nicely matches to a ground truth coming from SLID microscopy, showing you this cross-modality transformation. And we can quantify the improvement in resolution using nanoparticles. These are 20 nanometer fluorescent particles, imaged with a confocal microscope. If you zoom into some of these regions, there are closeless space particles that cannot be resolved. SLID microscopy can resolve them with a certain peak-to-peak separation at the nanoscale. This is why you have super resolution through an expansive microscope like SLID. And this is the neural network's output. taking the confocal microscopy input, beautifully giving you super resolution capability, nicely matching slid microscopy in terms of peak-to-peak separation of these particles. And if you look at the distribution of the point spread function, network's input is diffraction limited. It has a larger fluid half maximum distribution. At the network's output, it's shifted left, indicating resolution enhancement, and nicely matching the distribution coming from STED for the same sample. So this left shift is the signature of learning the distribution of the point spread functions that STED microscopy has. Perhaps one of the most successful applications of these cross-modality transformations has been on structured illumination microscopy. So these are examples of the same idea for different modes of microscopy. So at the input, we have a diffraction limited TIRF microscopy, total internal fluorescence reflection, total internal reflection fluorescence microscopy. It's diffraction limited. Because of that, you cannot reveal the fine features of these specimens. These are basically subcellular processes within a cell, and these are the timestamps imaging the same cell. Ground truth is using structured illumination at different angles of illumination with creating different interference patterns so that the higher spatial frequencies can be shifted to lower spatial frequencies and be retrieved within the passband of your system. So this is a computational system that is more delicate and requires 9 different exposures with different illumination patterns. And this one is showing the network's output from just the inputs shown here, beautifully matching the ground truth for every single time instant, super resolving all the features. These are, again, blind testing results. And this one is showing a movie of the same process. Every now and then it's stopping and showing you comparison of the network's input, diffraction limited TIRF microscopy. This is the neural net's output, and this is the ground truth coming from structured illumination microscopy. So these are generalization to new samples. We've also tested the generalization of the system to unseen types of samples. This neural network was trained with monolayer of cultured cells. That's why TIRF was very suitable for it. Now, after you train it, we said, let's now change the type of sample from cells to an embryo. Now you're looking at the same network's inference. When we, this time, capture images of a live embryo, Drosophila embryo, because of the nature of the tissue, live tissue, there's a lot more scattering. And you can see this with the fluorescence images shown here. At the network's input, you have quite a bit of change in the statistics of the input distribution. If you look at, for example, previous images, these are cells, and you have beautiful dark field, right? But here you have substantial deviation. Even then, the neural net actually works beautifully well, matching structural illumination microscopy without its hardware or without these interference patterns. And this is the movie of the same thing. This is a live Drosophila, network's input, network's output, ground truth coming from structural illumination microscopy, beautifully matching the ground truth. Here you have less photons, it's faster, so potentially less phototoxicity on the sample because you capture a single image at the network's input to reveal the super resolved images. So there are various different exotic transformations you can do with these ideas. I'll just touch base with this slide on one before I switch to another topic related to cross-modality image transformations. And this one is related to virtual propagation of fluorescence images. Oftentimes, if you're doing longitudinal experiments within an incubator, you come back the next day and you realize, hey, as you are capturing an image within an incubator, your cells are out of focus, or your microscope was working over the night, but it got out of focus, and some of the images are not usable. The things are out of focus. That might have happened to you. Rather than discarding them, actually, this framework gives you an ability to virtually propagate fluorescence images to on-demand different planes and different topologies, different surfaces. Here, the network is trained with out of focus fluorescence images, and there are in focus counterparts. But different than before, we are also appending your wish here, a digital propagation matrix. This tells you how you want to propagate, which other plane you want to look from this perspective. Let's say if this is your z equals 0, where do you want to go next? -8 micron plane, +3 micron plane, +8 micron plane, you name it. Through these DPMs, digital propagation matrices, you can take actually a single input image and virtually propagate it to wherever you want. After its training, it's actually learning the physics of the 3D point spread function of fluorescence microscopy. And we've shown that you can take a bead image like this and digitally propagate it to different planes. These inferences nicely match what you get from a standard scanning microscope. So this gives you the ability to virtually propagate fluorescence images on demand to different parts of your volume. We trained this with planar transformations. The DPMs were uniform, as shown here. Different colors refer to different axial distances with respect to your input plane. But you can actually, after training this, you can play with it with non-uniform DPMs. You can tilt your DPM, meaning that you can actually, instead of refocusing to a planar parallel plane, you can actually have a tilted plane. On demand, for example, we tilted the sample and applied a DPM that shows the tilt to correct at the output a tilted object. Sometimes you do an experiment and you don't carefully align it and it shows some tilt. From left side to the right side, there's a defocus. Those kinds of transformations now, after post-exposure, can be done on demand. Even a cylindrical surface, I would test it with a cylinder and with a DPM, you can nicely focus the entire thing that had cylindrical defocusing distances on demand. You have these kinds of things. This is actually quite striking to me because we never showed non-uniform DPMs during the training phase. This is purely generalization to different types of DPMs to cover different surfaces. And it works beautifully well with more complicated objects. This is a worm C. elegans that we have taken different regions of interest and virtually propagated it so that you can actually have sectioning on demand as you want. And you can take a single movie. Let's say this movie is a 3D movie where the worm is moving in 3D. It's out of focus in some parts. This is what you acquire. On demand, you can propagate this to different planes. So you can take actually the same movie and look at multiple movies that are virtually coming from different heights. So this is actually a very useful drift correction capability that you can have on demand after exposure of these kinds of images and movies. So in my last part of the talk, I will actually give you another a very challenging cross-modality transformation where physics, again, cannot put a forward model to be inverted. So when I talked about holography and Brightfield, how you can take a coherent hologram and reconstruct it with the contrast, spatial features, and the color contrast of Brightfield, that was one of those transformations where physically I cannot model with our current understanding of light matter reflection. As a result, data-driven learning was the only way. And that's why those results were obtained for the first time reconstructing a hologram with Brightfield contrast. Now, a similar story applies. I'll take fluorescence images this time and reconstruct them as if they were acquired with a Brightfield microscope. Fluorescence to Brightfield, we don't have that understanding of how those two quantities are related and how I can establish a forward physical model. That one in itself is extremely challenging, unapproachable from our current understanding. On top of that, to make the problem even more difficult than before, the object is going to go through a chemical labeling process. So the input fluorescence will be actually an auto-fluorescence process. It will be label-free, stain-free. And the Brightfield one will be Brightfield imaging after it's labeled. So not only the microscopy modalities are different in this transformation, but at the same time, the sample goes through a labeling process. So this becomes really challenging and nearly impossible for us to model. So we have to learn it through observation, through supervised learning. So you may be wondering, so what? What is special about this peculiar transformation? Well, if you could achieve this, you could actually change the workflow in histology. You could change the way that we process tissue for the last 150 years. So every time you give a biopsy, it goes through this laborious histochemical staining process. If you do not stain it with chromophores or fluorophores, and just look at it under bright-field microscope, it looks like glass. You cannot see contrast to thin sections of tissue. That's the same reason why, for the last 150 years, we stain this. We don't stop here. This staining process can take 2 to 3 hours for standard simple stains like H&E. But for more advanced spatial stains, it can take a couple of more hours, sometimes a day, such as for immunohistochemical staining. So our hypothesis is, well, let's stop the process here and forget about chemicals. And let's take an auto-fluorescence image of this label-free tissue. It gives you a grayscale image where all of these points here, they're revealing the intensity of autofluorescence at your filter. You can use DAPI, FITSI, whatever off-the-shelf filter, fluorescence filter you have. Without any labels, you're looking at fluorescence, autofluorescence contrast. And my goal is to transform these autofluorescence images and the contrast there into a stained version of the same tissue section as if it's coming from a bright field microscope. Cross-modality transformation, fluorescence to bright field, which is in itself very difficult, and label-free to label. That's where a convolutional neural net is helping us. So the architecture here is a generative adversarial network. That means you only have a painter here, the generator convolutional neural net, which is a unit structure. But you also have a discriminator, which is the critique, the main function of which is to regularize the generator to learn better virtual staining. So this is a competition between the two networks. The discriminator will try to understand if it's virtually stained by AI or if it's stained by humans through chemistry. Every time it can differentiate chemically stained versus virtually AI stained, generator is penalized and vice versa. This is not a standard GAN structure. This is conditional in the sense that the generator has structural loss terms, which regulates the generator to be structurally faithful. So it doesn't hallucinate. If you do not have structural loss terms, it will hallucinate. One thing to notice is this. This is not noise in virtually stained out. This is beautiful diffraction limited image captured by an autofluorescence microscope. It has the same resolution as the ground, not better. Those are very important. So I'll give you some examples of blind testing results from various different tissue stain combinations. Everything here is blind testing, new samples, new patients never seen by the network's training before. We'll start with salivary gland and H&E. If you look at the DAPI channel, this is the standard autofluorescence image of the thin section, 3-4 micron thin section. This is contrast enhanced for your eye. What goes in here to the neural net is BNF. It just shows you that there's some beautiful texture here captured. Very quickly, within seconds, you can have the H&E staining of the sample, nicely matching histochemically stained images of the same tissue sections, a couple of hours coming from histology lab, stained by humans. This is another stain, Jones-Silver stain. It takes longer to stain this. It's kidney tissue. Inputs are shown here, DAPI channel again. Beautiful resolution. Network's output for this Jones-Silver stain is shown here, and this is after 3 hours or so by humans. This is how it comes out from histology. Very nice match. Jones-Silver stain is a special stain and approximately 10 times more expensive, at least at UCLA, to stain compared to H&E. It's laborious. The technicians, technologist needs to look and examine it under a microscope. That's why it's more costly. But you have a beautiful match here with the neural net's influence. This is a third type of stain and two different types of new organs, liver and lung. This is Mason's trichome stain. It's again approximately 3 hours, as expensive as Jones silver stain. It's a special stain, approximately also 10 times more expensive than H&E. Liver tissue and lung tissue details are shown here in auto-fluorescence. Nice translation to Brightfield equivalent, nicely matching to histology coming from the lab. You can do this for more difficult transformations as well. These were chromophores staining tissue, but they were not molecularly specific. You can also have virtual immunohistochemical staining of tissue, IHC. Here I'm sharing with you examples of HER2. This is a human epidermal growth factor receptor 2. This is a key biomarker for basically the therapy of breast cancer, to choose different targets. This is a tedious process. It takes approximately 24 hours to get one of these things if you are the next person, your sample is the next. Typically, for us, it takes a couple of weeks to get our answers from histology, but the actual staining takes 24 hours. We've shown that you can take auto-fluorescence images, in this case, at 4 different channels, DAPI, FITC, Texas Red, Sci5. This is the superposition of those to reveal some beautiful virtual IHC matching histology, matching what comes from the lab after 24 hours of staining. So this is a great example where it's actually pushing it to much more challenging staining task, revealing. In fact, during the training of this network, we've seen that the ground truth is not ground truth because the humans, when they stain such a difficult task, they make quite a bit of errors. Perhaps 25, 30% of the time when we received the samples back from histology, they were actually wrongly stained. And I can talk to you more about that later. So these were some visual examples of how things are working, but visuals are visuals. At the end of the day, you need to also do the Turing test from the perspective of pathologists. So what we've done here is an attempt at that, where we have given our own images virtually stained of various different patients. And at the same time, we've given the standard histochemical staining coming from histology labs mixed with the same bundle. And without knowing which is which, they were actually scoring various different features, nuclear detail, cytoplasmic detail, extracellular fibrosis on these samples and giving us, scores. Well, we have got several of these tables in some of our papers that you can check, but the moral of the main message of the whole analysis is that there is basically, there's no statistically significant difference between the quality scores that we've got in virtual staining versus the chemical staining. The same is true when we asked them to blindly assess the patient's diagnosis based on these images. We've given these board-certified pathologists a group of patient images, some virtually stained, some histochemical stained, without knowing which is which. They have come actually with no clinically significant difference in their diagnosis made with our technology versus standard of care. That shows you kind of equivalence from the perspective of what diagnosticians are looking in these virtually stained images. There are many of these tables in this paper, supplementary information. Matching is great, but actually you're superior, virtual staining is superior in many different ways. And one of the most important advantages of virtual staining is standardization of staining quality. If you look at human histotechnologists and how they're staining tissue, you can see quite a bit of variation from run to run. This is expected, and this is just for UCLA Health. Everywhere around the world, you will see this variation. Deep neural nets are consistent. They have a certain style that they learn. If you want to change the style, you can change it. But once you lock it, it's consistent. So you don't have variations in the quality of the stain and its style. Standardization is very important. It's important for pathologists, but also it's important for downstream machine learning. If you want to do tumor margin detection, tumor classification, it will be a challenge to a neural net that does classification to learn how to work with these. It's not impossible, but it's doable. But what if you can actually learn better through a more consistent style of staining? And that's where I think we can offer advantages to other downstream machine learning tasks to be performed with our images. Most importantly, from a single cross-section, we can generate a panel of stains that are nanoscopically registered to each other because they're coming from the same microstructure. So which means a single unlabeled tissue section can generate a panel of stains. This panel here is not just an arbitrarily put panel. A lot of times for organ transplant rejection, you need this panel to diagnose the patient. And it starts with H&E because it's cheaper, faster, but later you go to the spatial stains. And that's where having them all on demand from the same cross-section is very valuable. Standard of care today is different sections. So you cut the tissue and look at different sections with different stains. It's a destructive process. It's labor-intensive, time-consuming. It's slow. And more than that, sometimes you deplete tissue and bring the patient back again for another biopsy. A lot of biopsies are unnecessary because we deplete tissue by chemical staining. What if we could all do this virtually so we don't have to stain and cut tissue again? That would be also transformative. So this is, I think, one of the biggest advantages. And for the first time, a pathologist will be able to see different stains and change them while the morphology remains the same. So they're perfectly aligned. CT has this already with different contrasts, but pathology never had this. What other forms of contrast can you use for virtual staining? Everything that I've shown you so far, it was grayscale, meaning auto-fluorescence intensity. Well, that's not the only way to capture label-free contrast from a tissue section. You can actually use quantitative phase imaging, holography. Our lab was also the first to use phase stain, meaning phase information of samples to do virtual staining. You can take all those beautiful holographic microscopes that we've shown that can do QPI, quantitative phase imaging. You can use them as a label-free contrast to do virtual staining, as we've shown here. This is how a QPI image would look with a holographic microscope, and this is label-free, and this is the virtually stained image, matching the stained version of bright-field microscopy image of the same section that is gone through the staining process. This is equally challenging because of the fact that coherent, single frequency, incoherent, labeled, all of those transformations are beyond the reach of our understanding of light matter interaction and stain tissue interactions. Another very exciting contrast mechanism is reflectance confocal microscopy, RCM. This one is special in the sense that this doesn't even have to take the tissue out. This is basically in vivo, and it's biopsy-free. This is a reflectance confocal microscope that can see through tissue. So you can actually, using this technology, you can utilize reflectance confocal microscopy images of the skin at different depths to do virtual, in vivo virtual histology by these virtual staining networks, all the way down to epidermis, dermal epidermis junction, and superficial layers of dermis. You can have them imaged with an RCM. RCM is FDA cleared for dermatology use, and that's why it's a great device for this purpose. We collaborated with Dr. Scampia's lab at UCLA to have these beautiful, and also Gene Rubenstein, to have these RCM images to be virtually stained for in vivo and label-free and biopsy-free samples. So finally, I'll finish off in the next couple of minutes by telling you that through these kinds of neural net transformations, you have a highway where you can start with a label-free contrast, mimic a histochemical label in histology through these microscopic transformations. But this network also enables you to do something more exotic. You can actually take a stained image and also transform that stain. So far, whatever I've shown you was label-free and virtual stain transformation. So this was already very difficult, but once I have achieved this for various different targets, then I can look into target-to-target transformations, like label-to-label transformations. That means you can actually take existing H&E images in our databases and transform them to other types of stains that were not generated because the tissue was depleted when you stained. So this is stain-to-stain transformation. And one of the biggest applications for something like this would be when the workflow already has H&E, because it's fast, cheap. When you have already H&E in your pocket in the digital world, you can take H&E and create spatial stains through networks that are trained by label-free networks. In other words, the label-free network here is the anchor point to do stain-to-stain transformation. One of the greatest applications for this is organ transplant rejection. So basically, what we've shown is that for certain patients, we ask diagnosticians to look at the case. These are basically needle core biopsies from kidney patients, and there's a suspicion of organ transplant rejection. So in a blinded study, we gave them H&E only images, histochemically stained, asked them to diagnose. After some washout period, we gave them H&E that's the same, histochemically stained, and the virtually transformed images. The hypothesis here is that they will be improving their diagnosis if they had this stain-to-stain transformation. And indeed, we've shown that we had approximately 46% improvement in their diagnosis, 48% concordance, and only 3 discordances, approximately 6%. In fact, one of those discordances was diagnostician error. With another referee diagnostician, we've identified that actually only 2 discordances happen. So it shows you how this stain-to-stain transformation can also be used to augment existing H&E stain into spatial stains. And something like this, organ transplant rejection, is very important because time is of the essence. To finalize, deep learning-based virtual staining of tissue saves expert labor and time. It eliminates reagents, training personnel, monitoring under a microscope, saves costs. It preserves tissue because we don't deplete it. It creates a platform where multiple stains can be virtually superimposed on the same cross-section. Through one cross-section, you can have multiple stains. And it makes staining consistent, mitigates variability in staining quality. Very important. So there is more push-pull between diagnosticians, professional, and us to further validate and advance this technology. So this is work in progress, of course. We made so much progress so far, but there's still a lot more to be achieved. We started a company from UCLA called Pictor Labs. Pictor in Latin means painter. So we're painting microstructure of tissue at Pictor Labs. This is a Santa Monica-based company, spin-off from our lab. And we've raised so far $19 million, approximately $19 million from VCs and different investors. And our goal is to transform histopathology, very much like Netflix transformed movie industry in terms of access to movies, right? Blockbuster days, you had to go to the store, one slide, one CD, one disc for each movie. Right now, actually, you can have anything that you want, all digitally on demand, and that's essentially the analogy here with Pictor Labs, how we believe histopathology will look like, especially when it comes to staining of various different kinds of tissue. To conclude, computational imaging and sensing, the tool set that we have behind computational imaging and sensing systems has dramatically changed thanks to deep learning. And now you can empower your field instrumentation, mobile instrumentation, to have high resolution, diffraction limit imaging capabilities, and also augmented with certain transformations that were not possible before, thanks to deep learning and the consistency of microscopy tools in general, letting them to reveal some of those transformations better than otherwise possible with physics-based tools. So with this, I'd like to conclude and thank you for your patience, and also acknowledge all of the funding agencies behind this work, our students and postdocs. Thank you very much.
Thank you for this fantastic talk. I don't truly appreciate it. A few questions. One is, neural networks have been around for, you probably know, 3 decades. What is novel in the deep learning that kind of make this field much hotter these days?
Great question. So I think you need to understand our computing tools advanced drastically. So first thing is the GPUs that I can buy for $5,000 to $10,000, thanks to gamers, thanks to Bitcoin miners, all of those, right? That didn't exist 20 years ago at that commodity level. So that means one of these things that I can train right now for a week in one of my $10,000 GPUs, you couldn't train that simply. It would take you 20 years, 25 years ago. I don't know how long, but you couldn't do that. And engineering is all about trial and error sometimes. So you got to have an empirical basis, and that's why cutting down the training time for certain tasks to a day was amazing. And of course, larger data sets. The other thing that's very important to realize is our image acquisition tools became drastically higher throughput, which means for generating 1 billion pixels now, it's a 1 hour experiment, half an hour experiment these days. That didn't exist before. So our access and our creation of high quality data and processing capabilities made simple, basic ideas from 50s, 60s shine in terms of learning. And I think microscopy is second to none when it comes to utilization of those ideas, because microscopy is consistent. Unlike macro scale imaging, unlike security cameras, unlike photography, a microscope is tremendously repeatable in terms of the spectrum, the way that the light is arranged, distances, illumination patterns. You're not having any unexpected things in the illumination and the image capture. That repeatability of optical microscopy, together with its throughput, high throughput optical microscopy, that made it a fertile ground for some of these ideas to really jump and flourish. Deep learning is based on error backpropagation, which was known for the last 50 years. Yes, but we didn't have the tools to utilize that for various different new applications. And so now this is actually a very fertile ground. During my talk, I mentioned that some of these are alternatives to physical methods, but actually there is more to it, which means physics can also be a regularizer. So the community right now is also trying to understand how physical lost terms that computer scientists perhaps didn't as much appreciate or work on, how those physical, for example, the wave equation in itself could help us also enhance learning through simple ideas like error backpropagation. And that's where there's also an intersection between physics, physical laws, physical understanding of light matter interaction, wave equation, etc., and learning through data. So data and laws of physics, they're kind of like now integrated into better learning. And those are some of the new ideas that make us get more out of this old framework of a neural network.
Thank you for the answer. Another question came in. Is it possible to detect nanoparticles less than 20 nanometers in size?
Yes. So with certainly fluorescence microscopy, you can easily do that. You can localize them. That's actually how Palm and Storm, any nano-localization-based microscopy technique is working based on those ideas. With the label-free techniques that I've shown, like the lens-free microscopy, these kinds of ideas, I haven't shown it here, but there are versions of this microscope. You see the mouse that I'm moving, right?
Yes.
So if you look at some of our publications, just type lens-free microscopy nanoparticle detection. you will see that there are versions of this device which is detecting nanoparticles and sizing nanoparticles. The limit that we achieved was, if I remember, this was several years ago, 30 to 40 nanometers, smallest particle that we were able to detect without any labels, using nano lenses that are formed using polyethylene glycol. So just look into that work where there's an attachment to this unit where you heat a container that has polyethylene glycol, and as it's evaporating, it's condensing on a substrate where the nanoparticles of interest are, and all of a sudden, it's like seeing through glass in a cold day from the home, right? You see some condensation, and that condensation helps you to understand all the dirt in your on your window, right? That's the same idea here at the nanoscale. So you can look at our work on nanoparticle sizing with these polyethylene glycol-based systems on Lensfree microscopy. The smallest was, I think, on the order of 30 nanometers that we detected, validated by SEM.
Thank you so much. Thank you so much. Regarding collecting your samples, are you looking into crowdsourcing?
So not for the deep learning based stuff, but for malaria, if crowdsourcing, we did some work perhaps 10 years ago on this, where to get the ground truth labels for malaria parasites, we did crowdsourcing. So quite a bit of my time at some point was dealing with malaria infected cells and using lensless microscopy to detect, quantify them. When you have a thin smear, let's say, yes, the diagnosis is made and you know that is a positive patient, but which cell is infected, it's a very difficult question to answer, because the diagnosticians are not very comfortable with that at the single cell level. So what we've done is this. We have created interfaces. You can look at this bio games. It's called bio games. As you can understand, we gamified biological microscopic imaging inspection, and in this case for malaria infected cells. So the idea is this. There's an interface. Unfortunately, that website is still up, but the game itself is not available, but you can find the papers that document how it's working. So we give every gamer, every participant in the cloud, without knowing their prior knowledge about malaria. Some of them can be experts, some of them can be citizen scientists. You give them a bunch of images where some of the images, we know the labels. So I asked diagnosticians to give me some labels for each cell. Through that, I have a channel of information to understand if this is a gamer that is serious, talented, or just randomly clicking. Based on the prior statistics that I collect, I weigh the decisions of the diagnostician, unknown diagnostician behind the cloud, a certain weighting factor. So those who are just randomly clicking, they're mathematically ignored. Those who are really competitive, because I know the labels for some of those images, let's say 15%, 10% of the images that I show them are labels that I know. And then the rest of the 90% of the images, I use their labels weighted with their confidence score, and coming from other diagnosticians, I come up with a final diagnostic decision. This was work that I did with one of my postdocs at UCLA, Dr. Sam Mavandad. So, that we have a couple of nice papers on this. The morale of the story is you can actually have a very accurate diagnosis at the single cell level by merging a group of mediocre diagnosticians and beat the best of the crowd. That's very important. You can beat the best of the crowd. I think it's a scalable platform for various different tasks. So if you look at bio games, malaria diagnostics, crowdsourcing, you can find related papers and the mathematical formalism behind this.
Thank you. One final question. As you mentioned, deep learning enables to understand some of the areas that is out of our nowadays physics knowledge. How the DL-formed solutions are verified when there's no concrete proof, which is still out of our knowledge?
Great. So it's true that we don't have a knowledge of the linkage, but the ground truth is still ground truth. I'll give you two examples. So here, the ground truth is a microscope. It's a bright-field microscope that in itself is multi-wavelength, and it's off-the-shelf microscope. Now, what is unknown is this: how do you relate the hologram captured at a single wavelength to the spatial and spectral features of the ground truth? That is the unknown. And that's where the learning through image data comes into play. How do I validate it is very simple, because I take my neural net's output and structurally compare it to the ground truth. Spectrally compare it to the ground truth, structurally and spatially. Well, in this case, as you can see, this is working because it matches. In fact, this movie is more important because it shows you that as you're going out of focus, let me full screen this. As you go out of focus here, even it works for out of focus objects and gives you a beautiful match to the ground. So that means even if you don't have the physical linkage between the input and the ground truth, you can actually validate it by looking at the ground truth. This was with this transformation, holographic reconstruction. And let me do the same thing with virtual staining, because it's even more difficult. With virtual staining, the question is like, yeah, I do not know physically how to relate this label-free auto-fluorescence processes to labeled version of a bright field image. Microscopy modalities are too difficult to relate, and also the sample goes through a transformation. I don't have a way to relate those. It's too difficult. Two things changing at the same time. But it doesn't matter for me because this is my ground truth. It comes from histology. In other words, a validation is depending on how, which setting it's going to use. Validation can be done even if you don't have this linkage in physical terms. And in this case of histology, virtual staining, validation was done in two ways. One, engineering way, which means you look at the structural similarity of your image versus what comes out of histology. You look at spatial resolution, distribution, color distances, etc. You quantify all of those with different stains. Then you also go to the second layer of validation, and that's the layer of the user. I call this pathologist Turing test. Can they statistically find the difference? And that's the second level of validation. Each neural net needs to be validated within the context of its users. And that's essentially what we've done with, after the engineering, the validation with pathologists blindly looking into our images mixed with standard workflow.
Thank you. Thank you for this fantastic talk, Aydogan. Truly appreciate it. Hope you get better soon.
Thank you very much. Thanks for having me.
Yeah.